Hey guys, in this video, I'm going to implement graph transformer with edge features. In my previous video, I implemented graph transformer which doesn't take into account edge features. However, in many real-world applications, edge features are important. For example, consider a social network like Facebook in which there is an edge between two people if they are friends on Facebook. However, different types of friends should have different importance and hence should be assigned different edge values. For example, the edge value of your spouse or your childhood friend or your close friend should be higher than the values of some acquaintance on Facebook. The model structure that I'm going to implement is taken from the paper, the same paper that I presented last time, a generalization of transformer networks to graph by Vijay and Xavier. However, I should point out that in this paper, they use point-wise multiplication between key and query. I'm not quite sure about the reason for that, because for me, when we want to compute attentions, it is more intuitive to use the usual dot product in which each query should be checked against all keys. So I will implement attention using the dot product of query and key. So here is model structures. The most tricky part in this model is to implement the attention module here. So before talking about the details of the attention module, I would like to review about traditional attentions. In traditional attention, we have query, key, and value. In order to incorporate the attention to give the output, we compute the so-called attention coefficients, which is created by the query and the key. So this is the softmax of query and key transpose divided by the square root of dimensionality of the key and the query. These attention coefficient will be used to give output. So the output will simply be the dot product of attention coefficient and the value. So now in our scenario, we want to compute the attentions in the context of a graph. So given a graph, we only want to compute the attention between two nodes where they are connected by some edge. Not only that, we also want to take into account the importance or the edge features of the two nodes. So here, the input to the attention module will be query, key, value, the adjacency matrix of the graph, and the edge features of the graph. So here the edge feature of the graph has size n and d, where n is the number of nodes, d is a dimensionality of the edge features. So in this matrix, E at the position ij is equal to the features of the edge Eij. So if I and j is not an edge, then Eij should be equal to O0. And then the attention coefficient will be created from query, key, adjacency matrix, and E, in which in this part here, we multiply query and key transpose, and then take the result, multiply pointwise with the adjacency matrix. Well, this part is to compute the attention only between the neighbor nodes in the graph. And after that, we will multiply pointwise with the edge features. So the attention coefficient in this case will be scaled according to the edge features. In my previous video, I didn't take into account the edge features. So that means all the edge values should have equal value that is 1. So this part in the previous video is just 1. But now we multiply the attention coefficient created by query and key with the edge features. The different things in this case here is that After you do this, then this attention coefficient will have shape N and D, in which this is not what we want, because the attention coefficient in this case is a d-dimensional vector, and we want to have just a single value. The way to convert a d-dimensional vector to a single value is simply take the sums over the last dimensions. So by taking the sum over the feature dimension, we convert this matrix into a matrix of size n by n. So now we get attention coefficient as scalars, and we can combine this attention coefficient with values to give output to the module. Now we will look at the structure of the attention module, which is this block here. For the input of this module, we need an adjacency matrix A of size n by n. We need a hidden representation of the node features, which are denoted by Hi, Hj here. This should have size n by the hidden dimensions. You can view hidden dimension here as the dimension of the model, D model. And we also need a hidden representation of the H features, which should have size nn and hidden dimensions. And again, note that the value at the point ij will be the features of the Heij. So in the first step, we will project these hidden representation of node features and H features into query, key, value, and H. After the projection, we will reshape query, key, value, and H according to the number of heads. And after that, we will use the query, the key, the H in order to compute the attention coefficients. So let me scroll down here for the details. First step, we simply reshape them into first and second step, we simply reshape query, key, value, and H according to the number of heads. In the third step here, we compute the attention coefficients as mentioned before. And in the fourth step is important here. We will aggregate along the H dimension to get the coefficient as scalars. And the final step, we will combine with the value V to give the output. The tricky part in the implementation of this module is in the fourth step. So after we compute the attention coefficient, which is this point here, at this point, there we will keep a copy of attention coefficients to proceed to give the output for the H features, and another copy is used to give output for the node features. So the output of this module will be node features and H features. And here we need to be careful at this step, because to give output for the node features, we need to aggregate over the H dimensions. But to give output for the H features, we don't make any change, and we simply pass it through a feed-forward neural network. So now let's not delay further, and let's put this into codes here. Well, I should have already import things here. Okay. So I also need NumPy, and we will create sparse multi-head attention module. For the init method, we need to specify the hidden dimensions. I will put the default to be 64. I would use 4 heads. We will initialize number of hits, hidden dimensions. So the first step here is to project the input into query key value and edge. So we need linear projection layers for the query, the key and value and edge. Key value and edge. And here I also want to have projection for the output. If you look at the diagram here, after we go through the attention module, we will concatenate the heads and then projection the output. So here I will combine this into this attention module. So I define the projection by OL for the head and OL for the OL for the node and OL for the edge here. So projection of output, let's say OH here means to get the output for the nodes, and OE is to get the output for the edge. Project. So we also need the same linear layer. And now we will define the forward method. So our input will be adjacency matrix A, hidden representation of the node features Hx, and hidden representation of the edge feature He. So here I will specify A is adjacency matrix of the graph, and it should have shape n by n. Hh is the hidden representation of node features, and its shape is n times hidden dimensions. Hidden dimension here is D model, if you are more familiar to that terminology. And He here is a hidden representation of the edge features. So before we pass the node features and the edge feature into the model, we need to pre-process them to get to these dimensions. He here should have shape n hidden dimensions. Next, we will extract parameters n, which is the number of nodes, the number of heads, and the dimension for each head. So n here is simply length of Hx, and H is self dot number of heads, and dh is self dot hidden dimension divided by nh. Now we will compute query key value edge and reshape according to number of heads. Q is self dot linear Q of the node features, reshape into n, dh, and h. And we do the same for key and value. For the edge, we will take on the hidden representations of the edge features. So it should be key value here, and the reshape here should be n, dh, and h. So next we will compute the attentions coefficients. Note that this is equal to qk transpose divided by the head dimensions pointwise multiplied with adjacency matrix, and then this value will be multiplied with the edge features. We will compute first the first part here, which I call the implicit attention coefficient. So attention coefficient implicit. Because the adjacency matrix is a sparse matrix, so I will use the API to compute batch multiply for sparse matrix, DGL SP BSDD MM Q K transpose, and we will scale this by the H dimensions. So after, so note that here the output size is N, N, and H. Note that we want to multiply this output N, N, and H by the H features that have shapes N, N, DH, and H. In order to multiply these two pointwise, we need to reshape this or broadcast this so that the third dimensions in this one is equal to 1. So attention coefficients in this case will be the implicit coefficients. You can reshape or unsqueeze, so I'm more familiar with reshape, and multiply with the H. So at this point, we have just computed the attention coefficients, which is this part here. And from this part, we will have two branches that move forward. One is for computing the output of the node features, and one is for the edge features. We will keep one copy for the edge features. So E out will be equal to this one. So keep one, give a copy for output of the edge features. And here I also want to reshape it to the original shape of the edge, that is NN hidden dimensions. So now we will compute the we combine attention coefficients here that we computed for this part. Okay. So first we need to take a softmax, but before doing the softmax here, we need to aggregate over the edge dimensions. So what I'm doing here is to aggregate over the edge dimensions, and the aggregation here, I will take the exponent of the sum. So take sum along. Note that the shape in this case it is NN, DH, and H. I want to take the sum over the DH here along dimension DH. So attention coefficients, I will take the exponent of the sum, in fact. Well, the reason is perhaps because there are a lot of zeros. So if we don't take exponent and take a sum, then we will get zeros. So to avoid getting zero, we'll take the exponent. But when we take exponent, the value might be big. So here for stability, I will claim the value to be between -5 and 5. So after doing this, we should have the shape that we want, N, N, and H. And now we will apply softmax. Now I think the N. So it will be the softmax of this over the last dimensions. So it should be dimension -2. We want to apply it over this dimension here. In fact, I waste a lot of time on this project because the default dimension for softmax will be the last dimension. And if we apply over the last dimension, which is the head dimension, then you will run into a problem. So you should apply over the second last dimensions in this case. Now we will combine with V to give output. So here in this case, what we want is we want to multiply this attention coefficients by the value that has shapes, in this case N, DH, and H, and we want to multiply by batch, that is along the last dimensions. I couldn't figure out functions that multiply by batch on the last dimensions, so I need to use a few reshape. So let me put down a note here. The attention coefficients here have shapes N, N, and H, and V has shapes N, DH, and H. The usual batch multiplication will multiply the batch along the first dimensions. So I need to reshape these so that NH become the first dimensions of both of these two. So here, to avoid writing out too many lines, I will do it in the multiplications. So first I will bring the head dimensions to the front. This can be done in two steps. So first we bring it in the middle here by swapping the position of these two, and then bring it to the outside by swapping the position of the first two. -3, and we do the same for the value V dot transpose 2 times. So, well, after you transpose, you should get the result here, which is a matrix of shape NH and DH. And to get back to the original form, you will need to bring back the NH to the last dimensions. But we also want our output to have the same shape as the input, which is N times the hidden dimensions. So here, after we bring back the NH to the last dimension, we also need to reshape this so that it is of the form N by DH times NH. So this will be transpose so we need to do the reverse of what we do earlier, -2 -3, and then we reshape this into N hidden dimensions. So well, at this point we are here. Right? So all that left is to project it at this point. So now we will do projection for both the edge features and the node features. So H out equal to self dot project H of H out, and E out will be the same. And we return H out, E out. Well, so that is a sparse multi-head attention module. Well, the next step, we will create the one single transformer layer. So graph transformer layers. Let me just copy this figure here so it's easier to refer to. Or maybe I will open it up for my, yeah, I already have it here. So let's put them side by side. What we have done is we have had the sparse attention module, which compute the output up to this point. Now, to create a single layer, we need to combine with all these add and norm and feed forward neural network. So last graph transformer layer, we will init this with hidden dimensions, default 64, and for it for the sparse attention layer. Self hidden dimension equal hidden dimensions. Shell number of hit is number of hits. So the first thing is to have attention module. Self attention equal to sparse multi-hit attentions. So in the computation here, we also have the attention module will reverse the output at this point. And here we have at each of these branch, we have add and normalizations. So we need to define two normalization here. The normalization are batch normalizations. So self dot batch norm for the node and n dot batch norm 1D hidden dimensions. And then we have second batch normalization for the node. For the edge, we will do the same. E1, E2. So the last component that we need here are the feed forward networks. So FF and H and FF and E. Each of these feed forward network is simply a sequential model that consists of three layers. First one is linear layer hidden dimension, twice hidden dimensions. The second one is ReLU activations, and then another linear layer that map back to hidden dimensions. In fact, you can play around with this feed-forward neural network and might have better performance. We do the same for the edge. Right, so that's all we need, and now we will define the forward method. For the forward method, we take in the adjacency matrix A and hidden representation of both the nodes and the edge features. First, we need to check n. Note that A has shape n by n, so n here can be A dot shape 0. So before passing hx and he into the module, we also need to keep a copy for all these skip connections. So keep a copy of hx, he for first residual connections. Here, there are two residual connections. The first one is from the original data, and the second one is at this point. So H1E1 equal HHHE. And next, we will feed the data through attention module. So we get output that I denote by HE. So at this point, we have H and E that are here. So they are ready for this block, that is add and normalizations. First block of add and norm. So H will be updated to batch norm H of H plus H1. For E, well, if I do the same, that is batch norm E of E plus E1, then I run into an error, because in this case, batch norm expect the input to have dimension 2, but my HE here has dimension 3. It's not quite that problem, but because here the way that I reshape is that I put the head dimension in the last coordinate. So batch norm assume the head dimension should be in the first coordinate. So to get it to work properly, I need to reshape this into a 2D module. And then once I get the output, I will reshape it again into the original shape. E dot reshape and hidden dim. So up to this point, we get the output here. And first thing, we need to retain a copy for the residual connections. So keep a copy for second residual connections. H2 E2 equal HE, and now we will fit through feed forward layers. So H is self dot ffn H of H, and E is self dot ffn E of E. Well, and then we have the second add and norm, second block of add and normalizations. So we do almost the same as here, so I will just make a copy. So this is the second one. Well, and we return H and E. All right. So that is one single layer. And now we will combine the layers to make a model, graph transformer model. So in this implementations, the model will take in the input as the graph. So we will feed this input through a collections of graph transformer layers, and on top of it, we will have a sum pooling layer, so that we will take the sum over all the node features for the classification problem. So classifier will be the last layer. Well, before feeding the input into graph transformer layer, in fact, we need to pre-process it, and we need to add in some positional encoding. The positional encoding that we use in this case is the Laplacian positional encoding. So I will guide this through the codes. So here, graph transformer model. So we need output size, which is dependent on the task at hand. So in this case, the data that I have is a binary classification problem. So output size should be 1. Hidden dimension default is 64. Number of heads is 4. Positional encoding dimensions I set to 10. So this is used in the Laplacian positional encoding for the node features. I will have maybe 4 layers of graph transformers. I also need edge dimensions. That is the dimension of the edge features. In this case, for the data set that I have, it is 3. Here we first need to have an encoder that give us a hidden representation of the node features. And in this case, I would use the built-in atom encoder to project the node features, let's say X, into hidden representation H. So atom encoder here, atom encoder into hidden dimensions. We also need to map the positional encoding into hidden dimensions. Right now, the positional encoding dimensions is 10, so we need to map it into hidden dimension 64. Self.positional encoding linear and n.linear hidden dimensions. We need to map the edge into hidden dimension as well. So self.linear for the edge. I will copy this from edge dimension to hidden dimensions. We need a stack of transformer layer of GT layers. So self.layer is simply a modulus of layers. So GT layers. So there are 4 layers in this case because we set the default number of layers is to 4. And lastly, we have before the classifier, we have a pooling layer which aggregate all the node features for classification. TGL and N, so we use some pooling. And lastly, we have a classifier. So classifier here is a simple sequential model. So I will take in the hidden dimensions. And feed through a few layers. In between the layer here, I use ReLU activation function. Well, the second one should be mapped downside hidden dimension by 2 times, and the last one we will map to the output dimension. Well, here I denote by out size. Alright, so now we have all the layer that we need. It remains to define the forward method. So for the forward method, we take in a graph object G. We take in node feature X. We also take in the positional encoding of the node of the graph. So first, we will create the adjacency matrix based on the graph. We take the edge index and create a sparse matrix from the edge index. So n here is the number of nodes. A here is sparse matrix created by the edge index. Now we will get the hidden representation of the node features. So first we map the node features into hidden dimensions, and then we add with the positional informations. Okay, so this is hidden representations of node features. We also need a hidden representation of edge features. Well, the edge feature in this case can be accessed from g.edata feed. We not only want this, but we want to map these things into the hidden dimensions. Right now, this original edge feature has dimension 3, and we want to map it into hidden dimension. We need linear E. So this is to map the edge feature into hidden dimensions. Well, in fact, this linear layer only apply on float data. So this data is in integers. We need to convert it to float. The output at this point should be number of edge times the hidden dimensions. This is not the output that we want. We want the output of the form n hidden dimensions. In order to do that, I will create a sparse matrix which take indices as the edge of the matrix, so edge of the graph G. So the indices are here. We simply call the function, these functions. In this case, we want to specify the value as the edge features. And I will convert this matrix to dense, because at this point we have a sparse matrix with shapes and hidden dimensions. By converting it to a dense matrix, we can use it as before. Well, this is the part which slowed down my computation quite a lot. I am not sure whether there's an API that deal with this multi-dimension sparse matrix. So yeah, I need to convert to a dense matrix, because I'm not sure, I'm not very familiar with the DGL library. So now the input preparation is done. We will feed these through the graph transformer layer in self.layers. Yeah, I call this self.layers. HE equal to layers AHE. On top of this, now we use the pooler to aggregate the node features, and then classifier. So, and then get the output. Alright, so that is it for the graph transformer model. All that left is to apply this model and train for some particular data. To avoid making this video get too long, I have already loaded the data here. So I use the same data as in my previous video. This is the data for graph classification problem. Well, unfortunately, I do not have a GPU in this video. In the last video, I was able to use the GPU for the diffgraph library from Colab. However, Colab have updated something that make the same installation not working anymore. So I have to use CPU in this video. For that reason, I need to downsample the dataset in order to train it on a CPU. So I will use 2000 graph for training, 1000 for validation, and 1000 for test. The batch size that I use is 32. So this is for the data. For positional encoding, I use Laplacian positional encoding. So the encoding dimensions is equal to 10, and this is same code like in the previous video for Laplacian positional encoding. So basically, Laplacian positional encoding in this case will factorize the Laplacian matrix of the graph and pick the 10 eigenvectors that correspond to 10 smallest eigenvalues to encode the positions for the nodes of the graph. So now let's go to the train and the evaluations. For the train loop, we take in model, loader, loss function, optimizer, and device. So total loss is zeros. We want to return the loss. For I batch labels in enumerate loaders, first we will convert batch and label to the correct device. If you have GPU, then this will be very helpful. We will compute the predictions of the model. So the model will take in the input as the graph. In this case, it's a batch graph. The features of the nodes in this case is assessed by n data, and the positional encoding of the node, which we created here, and it is in the n data PE. So this gives us the logit for the predictions, and the loss is a function between these logits and labels. Well, here we need to convert label to float. Then we can optimizers zero grad loss backward, optimizers step. So the total loss will be updated. Let's also print out some informations. So for every 20 iterations, or when we reach the end, we will print out the loss. iteration I loss. Let's print them out up to 4 decimal places. So we return the total loss. But here note that we also need to divide by the number of batches. This is the chain loop. For the evaluations, I will use the ROC AUC API to evaluate the model. Well, in this case, ROC AUC is a better measure than the normal accuracy because for the given data set, it is very skewed. There are a lot of class 0 and only few of class 1. So if we use a usual classification, which is accuracy, and if the model always predicts 0, then it is guaranteed to be a good model. So the measures of evaluation is ROC AUC. Basically, in this evaluation, not only it take into account the correct prediction, it also take into account of the wrong predictions. So it penalizes also the wrong predictions. It is a better measure in this case. So we want no graph. We don't want to check the gradient in this case. So we will loop through the loaders. If you have a GPU, this is helpful. Let's convert all this to the GPU. Y-head will be the output given by the model. And Y2 is we will append Y2s with the correct label. And predictions will be append, we simply append the logit is Y-head. Right, so this part is to make sure that they have the same shape. So after this, we will concatenate them. And convert the type to NumPy, because this could be fed as input for the evaluator. Same code. Our output in this case is a dictionary with keyword Y2 and Y prediction. And the score in this case is an evaluation on this dictionary, and we take the score. All right, return score. So the evaluation, again, we get the ROC AUC score. Now let's put everything together. Train and test. In this train and test functions, take in model, train loader, validation loader, test loader, number of epochs loss function, optimizers, evaluator, and device. Well, we want to keep the best model. That is the model that performs the best on validation data. So this is the best validation, ROC AUC, best model equal to none for epoch in so here let's use the QDM, so it gives us some information on the process of the training. Description here is epoch. Print out the epoch training. Well, let's call the train functions. So we train for one epoch, get the train loss, and then we evaluate the model after training for one epoch. So so we evaluate it first on the train data set. This is the evaluation function. But here I want to do it on the train data set. We evaluate it on the validation data set and on the test data set. Well, maybe we want to save the best model on that give the best performance on the validation data set. So if the validation result is bigger than the best validation result, we will make a copy of the model. Deep copy model. And well, we also change the best validation result to the current best. All right, after one epoch, we should print out some information. Let's print out the chain loss. Print out the chain score. We also want to print out the validation score and test score. We would like to see how they change when we are training the model. And we will return the best model. All right, so well, that's it. Let me see, I have some error. Match labels in loaders. There should be a for loop here. All right, so now all that left is to train the model. The evaluator here is API evaluators for our dataset. We will initiate the model, set the device. I don't have a GPU, unfortunately. Loss function, which use BCE with logits. This is more stable than the usual BCE with the logits applied on the output. Optimizer is the standard ADAM optimizers. Learning rate is a standard learning rate. Maybe before we train it, we want to print out the pre-trained performance of the model, so we can compare how the model improve through the training. So we want to print out all the score before training. Okay, so here is a pre-trained performance. So you can see that before training, the score for the train loader is 0.35. For validation data is 0.35, and for test data is 0.24. The train take quite some time, so here I will just not do it in the video, and I train it for 5 epochs. So you can see after the first epoch, the train score is improved to 54%. So before training, it is 0.35. After one epoch, is already improved to 0.54. And we also see some improvement in the validation and the test scores. After 5 epochs, the final score for the train is 0.78. The validation is 0.55, and for the test is 0.62. This is pretty good. Consider that we only train for 5 epochs, and we train on a small fraction of the dataset. So that's it for my video today. If you have any comment or anything that you would like to discuss, please drop a comment in below.